Thank you very much for the kind introduction. First, I would like to thank organizers to invite me to this nice and interesting workshop. So I'm Koji Ishibashi from Riken Institute in Japan. Yeah. First of all, I have to introduce my group members. Actually, the work I'm talking about is conducted. Oh, sorry. No. Yeah, by this guy, Russell Riken, who is a research staff member in my group, and also the postdoc Mike Randall for the topological insulating material, and Hosoda-san, who is from Fujitsu company, collaborating with us, also working on topological insulator tungsten diterite, and Patrick Serkins, who worked on semiconductor nanowires as a topological insulator. So, yeah, of course, the long-term, I will talk about the experimental work with semiconductor nanowires with large spin-orbit interaction, and also the two-dimensional topological insulators, tungsten diterite mainly, and those materials are coupled with the superconductor, ordinary S-wave superconductors. Then we want to realize with these materials, we want to realize one-dimensional helical channel. I will explain this later, contacted with ordinary S-wave superconductors. Then, yeah, this is an interesting topic, subject, we think, because if the topological transition occurs, it can be a one-dimensional topological superconducting channel where the so-called Majorana zero mode would appear at the edge of the 1D channel. And this Majorana zero mode would be used for the Majorana qubit for the topological quantum computing. So still, this is very fascinating, but very, very wrong way to go to realize this. So we are just beginning stage to study basic physics to realize the one-dimensional helical channel and which are induced superconductivity. So, I just want to show, I want to tell you how interesting the Majorana qubit is, even though this is very, very far away. Maybe I will retire before this is realized. Yeah, so this is image of Majorana qubit made of 4 Majorana particles, and someone is manipulating this particle. So very complicated topology, so that's why they call it the topological manipulation. So the nice thing of Majorana qubit is ideally no decoherence, immune to noise, which should be very nice. We heard in the previous few talks about superconducting qubit and any other qubits, always the decoherence is a problem. So from the material or device level, if we could solve the decoherence problem, it would be very nice. But of course, Majorana has not been observed in yet. So it's, this is the person who predicted the existence of Majoranas, and this theorist in Caltech proposed, suggested Majorana would appear at the end of one-dimensional atomic chain. Yeah, kind of a mathematical model, the so-called Kitaish model. So this is just my experimentalist understanding of Majorana. It's maybe too simple. The theory should be more complicated, but anyway. So Majorana particle, it is predicted to exist basically in high energy physics, so it should be in vacuum. But recently the interest is in the Majorana particle in solid state materials. So definition of Majorana particle is expressed by this. If the creation Majorana operators like Fermi operator C or C dagger. So particle and antiparticle are same. So antiparticle means that just charge is different. Other things are same. So if you think about semiconductor, solid state, maybe electrons, simply speaking, the electrons antiparticle could be a hole. Of course, in semiconductors, electrons and hole are very different. In addition to the charge, the effective mass, mobilities, those are different. So it's not, hole is not exactly the antiparticle of electron. But if you look at this expression, Majorana particle is a combination of electron and anti-electron, maybe hole. Yeah, this is electron and hole. So very roughly speaking, it's a Majorana particle is half electron, half hole. Superposition of electron and hole. Yeah, something like that for my understanding. So, so this kind of half electron, half hole may exist in superconductors. Actually, in superconductors, there is a superconducting gap, and the excitation of the ordinary superconductor is the quasi-particle. So this is the electron-like quasi-particle and hole-like quasi-particle. And these two, electron-like, hole-like quasi-particle have particle-hole, so-called particle-hole symmetry. That means the electron-like and hole-like quasi-particle are very similar. You can think it. The electron, Cooper pairs around the electron. This can be seen as one hole with one extra Cooper pair. So number of Cooper pairs are not important in superconductors. So electron particle-hole symmetry is met in ordinary superconductor. But this is not a Majorana particle because Majorana is 50% superposition of electron and hole. So you see, obviously, this particle is more electron